So first we need to specify the pre-transform. The pre-transform is something that you can use to transform the image of the swap chain. For example, rotate it by 90 degrees or by 180 degrees. The way we're going to fill this in is by just querying the surface capabilities, and then we'll supply the data to the info struct. 1 second, I forgot to show you the attributes of the function. So the VK API attribute, what is that? On Windows, it is nothing. The VK bool should be obvious. It's just a uint32t. The VK API call is just a std call on Windows. So yeah, I still think these are very confusing the first time you see them. But yeah, now you know what they are. So let's continue. In order to fill in the pre-transform, we check the surface capabilities, which is called vk get physical device surface capabilities, KHR, which needs a GPU, vk context, GPU, a surface, and surface capabilities. I call these surface caps. Find those, vk surface capabilities, surface caps. Is 0. Quick check. Does it return a result? Yep, it does. So we do vk check against that too. Run that real quick. See if that works. It does. Good. Is surface caps dot. And then we can look. Oh, we have a current extent, current transform, min max image count. We need the current transform. We also need more, which is why we do this call. For example, we also need info dot image extent is surface caps current extent. Boom. Remember how I talked about that swap chain can have different image counts? We need to specify that when creating the swap chain. And you do that by looking at the surface capabilities. The surface capabilities return a minimum and maximum image count. Going through tutorials myself, they advise you to use min image count +1 if that doesn't exceed maximum image count. So we're going to do uint32t image count 0, and then image count is surface caps dot min image count +1. Then we're going to check if the image count is greater than surface caps dot max image count. We're going to do image count -1. Otherwise, we're going to use image count right then and there. And we assign that to obviously image count. And I suppose we could initialize this over here. Then we supply that to the info image count is image count, and check the next validation error, because we are going to get more, I suppose. Let's see. So the next problem we get is that composite alpha cannot be 0. Okay, I like to specify this here. scInfo.composite alpha is, and what this is basically asking us, how the alpha value should be treated. I have always been using vk composite alpha opaque bit, meaning that alpha value is ignored. This might not be correct in every case, because this basically means when you specify an alpha value in your color, it is being ignored. So for example, let's say you load a texture and then you sample from that texture and try to display the value, and you make the texture 50% opaque. In the alpha channel, this is being ignored and it will be 100% opaque. So keep in mind that this can result, and it has been for me, in confusion. I'm going to use alpha opaque bit right here. You can also use different ones, and I encourage you to play around with different values. So yeah, looking at the next error, image array layers cannot be 0. Again, okay, we're just going to specify scInfo.array layers to be 1. And then it's basically talking about opaque bit alpha. Okay, build that again and run. See what happens. Still a problem. Let's look. This time it is complaining about the image format. We have no format specified. This is basically the format the image will be displayed in. Let me show you what that means first and then explain the format. I think that makes more sense. In order to specify the format we want to use in the swap chain, we first have to check if we actually support a given format. And we can do that by querying, again, information from the GPU and the surface. We do that by calling vk get physical device surface formats. We obviously need the vk context GPU. We need the vk context surface, the format count, specify that as a pointer, and null for the first call. And for the second call, we specify the surface formats. So uint32t format count 0 and vk surface format khr surface formats array of 10 as the array. And then again, the to-do sub allocation from main memory. Again, you can use an std vector here. It is up to you. I just like to do it this way. Once we have the surface formats, we need to loop through them. Oh, and by the way, let's check if these have a return type of VK result, which it does. So we need to do VK check on those. Okay, now we loop through those. For uint 32ti is 0. I is less than format count, I++. I like to do VK surface format, KHR format is surface formats on I, and then do an if check. If format dot format is the same as VK format. And this is where I've done some digging, and the format B8, G8, R8, A8, sRGB is the most common one, according to this website, vulkantutorial.com, of which one the most common one is this one. So yeah, we are going to use this if we get it. And you should be able to get it. If you don't, then maybe write that down in the comments and I will try to fix that. But I assume that this will work for everyone that's watching. It worked on my 10-year-old laptop, so yeah, should work. And I like to save this format for later because we need this later as well. So we do VK context surface format is format. After that, we break out of the loop. And then we specify this here, image format, which would be VK context surface format dot format. Let's define that up here. Let's put this below the VK surface format. Let's put this below the surface. And yeah, we added the format here. Boom, and see what we need now. Actually, this works. Nice. It's probably still throwing a bunch of validation errors, but now we created a swap chain. Oh, wow, there's no errors. Well, what do we need now? Well, now we can actually retrieve the images that the swap chain was created with. We do that by doing vk get swap chain images. What do we need? Well, we need a VK context device. We need a swap chain, VK context swap chain, the image count. This is basically the same thing. We query the count, then we get the images, and the images will be 0. We copy that, paste that, and we store those in the VK context swap chain images, SC images. And I made a mistake. This has to be VK context as well. VK context image count, VK context image count. And let's call this SC image count. I like this more than image count. Okay, go up here and define those. By the way, let's put the debug messenger below the instance. And I like to do a tiny bit of separation here. It's just for me that I can read it better. The first thing is the uint32t swap chain image count that we specified earlier. And then the VK image array. It's like swap chain images. And of course, let's also add the to-do here. Sub allocation from main memory. And this has to be an array. I specify this as 5 because I know I don't have more than 3. Again, if you want to use std vector, you are very welcome to do so. I've been using vector for the longest time myself and I don't see no harm in it. I just try to practice this way of programming and see where that leads me, which is why this might seem weird to you. Okay, we get those. They are probably result calls again. Okay. So we do vk check against those, please. Check if that works first. Yep, it does. Good. In Vulkan, you can't use images directly. You need what is called an image view. The image view describes how you look at the image. The image is just memory in the GPU, and the image view tells you how this memory will look when you look at it, let's say on a screen, right? You can specify, well, this piece of memory is a 2D image, which is a flat image. It has one level and one layer and so on, right? I just tried to understand why I would actually need those image views for the swap chain images. I will not be creating them now to test if my application runs until I actually need those. Now, let me point out, we probably need them, but I don't know and I want to test out. And I want you to get into the same habit of just trying out if something works or not. Because again, in my opinion, this is the best way to learn stuff. So I want to learn now if I actually need the swap chain image views and when I need them. We call the swap chain done for now. And now we can actually do a bool vk render method, which will probably take any vk context, pointer vk context. Let's talk a little bit about what we'll do in the renderer. Let's talk a little bit about what we'll do in the render loop. We will ask the swap chain for an image. The swap chain will give us this image. We then create a what is called command buffer. This command buffer is there so we can record rendering commands. The first thing that we will do is a command to clear the image into a color that we specify. Then we end the command buffer. We then submit this command buffer work that we recorded to the GPU. And after it has been submitted, we present the image on the surface, which is basically this, right? Bloop. We then need to wait on the GPU to finish the work, and we will loop over this again and again and again. This is the render loop. Obviously, we have to do some synchronization, and we'll find out what we need by just letting the errors tell us. So the first thing we need to do is vk acquire image, not image2, but khr. Again, the 2 is a different version. Almost the same, but not exactly. And if you want to know more, I highly recommend the Vulkan Discord server. It's probably the best place to ask. So yeah, anyways, vk context device. We need a device here. We need this swap chain. And then we see a timeout, a semaphore, a fence, and an image index. We are not going to specify anything but the image index for now. And we'll see what happens, right? We need the image index, which is a UN32T image index. And obviously this is a vk check again. Then we do the rendering commands. And after the rendering commands, we do vk q submit. We now submit the work that we recorded to the GPU using the queue that we specified earlier, the graphics queue. So we do vk context, graphics queue. Well, we need a queue. But now we notice, oh, we need a queue, not a queue index. Remember when we created the logical device? We specified a graphics index for a queue create info, but if we didn't do that, we got the access violation error. When we create the device, it implicitly also creates the queue that we can use in the submit call. We just have to get the handle on that. We can get the handle by doing vk get device queue, not 2, but 1. What do we need? Well, we need the vk context device, the family index, vk context graphics index. The queue index is 0 because this is the first queue. And then the pointer to the queue, which will be created, is vk context graphics queue. Quick check, is this returning a vk result? No, it isn't. Add the graphics queue below the device, vk queue graphics queue. And let's go back down here. We do the graphics queue. Next, it's asking us for a submit count. You can submit multiple recordings, but we are going to submit 1. And then obviously the pointer to the submit info, which is again a struct submit info, and a fence, which will be 0 for now. We'll see what this does later. And this is definitely a vk check. We're going to do this immediately. Well, we need a submit info, which is a vk submit info. Initialize that to 0. Let's fill this in real quickly. Submit info dot s type, probably, yep. vk structure type submit info dot. What else do we need? We have a command buffer count and a pointer to command buffers. We will need that for sure. And then again, semaphore count, wait semaphore count. We will use this later. So submit info dot command buffer count would be 1. We use 1 command buffer. Submit info dot pointer command buffers would be pointer to CMD. We'll create that in a second. After that, we do a vk queue present. Again, we have to specify the vk context graphics queue and a present info pointer. Present info. This is a vk present info. KHR present info. Initialize that to 0 as well. Present info dot s type. Again, vk structure type present info dot. What do we need? We need a pointer to the swap chain, a swap chain count. Let's do that first. vk context swap chain present info dot swap chain count is 1. What else do we need? Nothing really, except the pointer to the image indices, which would be the pointer to image index. And this, of course, is a vk check again. Okay, now we actually do the rendering commands. First, we need to create a what is called vk command buffer. In this vk command buffer, you have to allocate those from command pools. Let me show you. vk allocate command buffers. We have to specify vk context device and allocate info, which would be alloc info, and then a pointer to the command buffer, which would be CMD. Okay, so let's create this vk command buffer allocate info, alloc info. Initialize that to 0 as well. Alloc info. What do we need? S type is obvious. vk structure type command buffer allocate info, alloc info dot. We can specify the command buffer count that we want to allocate, which is 1 alloc info dot. Now we need to specify the command pool, which we don't have yet. vk context command pool. We need to create the command pool so we can allocate command buffers. And we do that up here in the vk init function. Command pool. Create a local scope. And then we do vk create command pool. What do we need? We need a vk context device. If I can spell device, let's do a pointer to pool info. Allocator 0 again. Command pool, vk context, command pool. And this definitely is a vk check. Let's first go ahead and create the command pool real quick. vk command pool, so we don't get any errors down here. Go back here. We need the vk command pool create info, pool info, initialize that to 0. What do we need? Pool info, well, S type is obvious. vk structure type command pool create info, pool info dot. Okay, this is interesting. We need the Q family index, which is the vk context, and I think that is actually it. We're going to check that out. Looks like I did something wrong. Oh yeah. Whoops. I forgot to specify this as a pointer. And down here we have the problem that the command buffer is in the local scope. Put this up here and this one too. And I've done a mistake. The rendering commands will be inside once we started the command buffer, which we have to do by vk begin command buffer. And as you can see already, it has a vk result. We will check against that and also the allocate command buffer. Okay, what do we need? We need the cmd, the command buffer, and a command buffer begin info. Let's call this begin info. Do the vk check here. And I forgot to do the vk check here. It's very easy to forget this. Okay, so vk command buffer begin info, initialize that to 0, begin info.s type, again vk structure type command buffer begin info dot. Let's see what we need. We have flags and an inheritance info. I know that we need flags. In the flags you can specify bits, and we want to specify the bit that this is a one-time submit command buffer, meaning we allocate and submit this only once, which would be vk command buffer usage one-time submit bit. After calling begin, we also need to call vk end command buffer, pass in the cmd. And this also returns a vk result. So we check that. Now you noticed we called allocate command buffer. If we don't free it here, we will leak memory every frame. So it is very important, and that happened to me in another application, which is why I'm pointing that out here. We have to call vk free command buffer. Don't forget this. vk free command buffers. We pass in vk context, device, the command pool, command buffer count, and the pointer to this command buffer. Quick check. This doesn't return vk results, so we're golden. And my mistake, we can't free the command buffer unless we submit. And even later, we can only free the command buffer when it is not in use. But I will keep this here, and we will compile and see what that means in a second. Before we can run the program, I forgot, we need to call vk render, and we pass in the vk context as a pointer. I've set the breakpoint inside the render loop. Boom. And obviously all of these should not fail. Boom. We try to free and then we do a Q submit, and it should give us a validation error, which it does. If command buffer count is not 0, pointer to command buffers must be a valid pointer to an array of command buffer count valid vk command buffer handles. This is in the submit info. So it is telling us that we should not free the command buffer before we submit to the queue and also present. This command buffer has to be valid until the device is done. And the way we can do that is by doing vk device wait idle, which is vk context device. This will wait on the device until it is no longer processing. And then we can free the command buffer. Yep, this also returns a vk result. So we do vk check. Let's compile again and see what is happening. This first one is telling us that we don't specify a semaphore and a fence at the same time. We can't do that. We'll do this in a second. We allocate the command buffer. We begin the command buffer. We end the command buffer. We do the submit. We get another error that we'll handle later. We wait for the device and then we free the command buffer. Okay, so we remove the command buffer error right here. Obviously, we'll do more synchronization later, but for this very simple example, this will be enough. Okay, let's tackle the synchronization. This can be a very difficult topic, but I'll try my best to explain how I like to think about it. First of all, if you don't know what a fence is, I like to think of fences in terms of front-end synchronization. I try to connect the F to something that is CPU related. I call fence the front end, which means the CPU will wait until the GPU is ready. This is front end synchronization for me, in my opinion. Basically, you do a Vulkan command, which will do work on the GPU, and then you wait on that fence on the CPU until the GPU tells you, yes, I'm ready. A semaphore, on the other hand, is a back-end synchronization, meaning you have different Vulkan commands, and the order in which you type the commands in your code does not mean that they will also be executed in that order that you specify them in the code. They can be done at any point in time. If you want that certain operations finish before other operations on the GPU, you have to specify semaphores to tell them, well, if you want to do this, you better wait on on the other command until it is finished, and then you can do this command. The best example that I can give you is the submit and present. We can only present an image to the swap chain if we have actually done a submit to the graphics queue beforehand. So I think the best example would be to start here. So how can we achieve the synchronization between submit and present? There is a pointer to signal semaphores, meaning that when this is done, we will signal a semaphore that we can wait on in a different command. So we signal a semaphore here, and in the present info, we wait on a semaphore, and those two will be the same. We signal it here, we wait here. Let's add that semaphore real quickly to the VK context, which is a VK semaphore. I like to call this the submit semaphore. Back down here, we wait on the VK context submit semaphore, and over here we signal the pointer to the VK context submit semaphore. Don't forget, we need to do the submit info dot signal count, signal semaphore count, which would be 1 over here, and also the wait semaphore count here, present info dot wait count is 1. We wait on 1, we signal 1. The count is very important. Don't forget that. That is the first way to do synchronization between those two commands. We also have to synchronize the acquiring of the image and the submission to the queue. Basically, when we acquire an image, we signal a semaphore that tells the GPU that submitting is fine. So we do VK context acquire semaphore. Let's specify that up here. VK semaphore acquire semaphore. And then the submit info dot wait semaphore count is 1, and submit info dot pointer wait semaphores is VK context acquire semaphore. Don't forget the semicolon here. Before we can actually run this, we have to create these objects. I like to call them sync objects. We basically just create VK create semaphores. What do we need? VK context device, semaphore sema info, allocator 0, and VK context acquire semaphore. Yank paste that. We need 2. We need to create 2. The next one is the submit semaphore, VK semaphore create info, sema info, initialize that to 0. Well, what do we need to specify? Sema info dot s type, VK structure type, semaphore create info. Let's check the other stuff, sema info dot, and I don't think we need anything, so let's not use that. Oh, and also we need to specify the address to those here. And also we need to do VK check as well, like this. Let's see what types of errors we get now. Open the debug console here, acquire the image. Seems to work fine. We allocate the command buffer. We begin the command buffer. We end the command buffer. We try to submit. Interesting. We get a pointer submits wait stage mask specified at 0. Okay, so we still have one more problem. Let's see if the present works. The present is complaining about the image layout that we use. We are not changing the image layout yet because we don't call any shaders or anything, which makes sense that it's complaining. Then we wait for the device to be idle, and then we free the command buffers. Okay, so the last thing we need to change is the pointer to a wait destination stage mask. Let's call this wait stage. A quick check what that actually is. Pressing F12 here. VK pipeline stage flags. So over here we do VK pipeline stage flags wait stage, and that is VK pipeline stage color attachment output bit. I had to look that up. This is basically what we have to specify. There is a shit ton of stage flags over here. For example, the easiest one is vertex input, vertex shader, geometry shader, fragment shader, all of those. Color attachment output is right here. Compute shader. We want the color attachment output. Let's build that again and try to run it one more time. Real quick. We acquire the image. We allocate the command buffer. We bring it in the command buffer. We end. We submit and we present. And we only get this one image problem that we can't fix for now. Great. Now we can finally do clear color. This is the first and only rendering command we'll do for now, which is VK CMD. The rendering commands always start with VK CMD. And we have the first one here already, which is clear color image. Boom. We need the command buffer. We need the image, which would be the VK context swap chain images on image index, right? We basically use the swap chain image. Well, what type of image layout do we want that to be? VK image layout. And let's try to see if it actually changes the image layout. It's specifying that it needs to be in present. So we do present source KHR. We need to specify a pointer to a color, clear color value, a range count, and a pointer to ranges. Let's call this range, pointer to range. Well, what is that exactly? All of that. The color should be intuitive. VK clear color value, color, and we can specify in ints the value that we want to do. let's say the 1, 1, 0, 1, right? The first one is the red channel, the second one is the green channel, and the third one the blue, and the last one the alpha, I think. Now we have the color, and the next thing we need is a VK image sub resource range. Let's see what we need in the range. This time no S-type, but we need a layer and a level count. They are very important. Layer count, level count. Basically the same stuff that we specified when creating the Swapchain images. Range. Okay, and the last thing we need, which I know is the aspect mark, which is VK image aspect color bit. Then let's try to compile. I'm going to remove this breakpoint and run that. And it's yellow. Yeah, we did it. Obviously, we still have a bunch of problems like the VKQ present and all of that stuff. We basically destroy the window before we present. And in the console over here, we have the problem with the image layout that is not correct. So yeah, the image layout here doesn't do anything. It took us about 300 lines of code to successfully change the background color of our window. While this seems much, in my opinion, you only write this more or less once. And you can get a very clear picture on how Vulkan actually works. And when you get through this once, it is not that difficult to continue. Obviously, we have not touched on render passes yet and pipelines, which is what I want to do next. But I hope this shows that we don't need this much code to get something showing on screen. And again, you more or less have to write this once, and then you can create yourself helper functions that will aid you in your Vulkan work. For example, what I mean is, let's create a new file called vkinit.cpp. You could also use HPP. I'll just use CPP as an example. It doesn't really matter. And then you'd go ahead and do this. You copy the begin info, you paste that here, and then you create a function out of this. Well, we yank a word, we paste that here. We do cmd begin info, put this in here. Obviously, we need to include Vulkan, vulkan.h, and then we return begin info. And I like to call all of these info. This is basically the first thing. And then in the renderer, we can do vk command buffer begin info. Begin info is cmd begin info. Don't forget to include that over here. Include vkinit.cpp. And then I need to learn how to spell this begin info. And I just noticed my render function doesn't return true in the end, which it should. We can now run the program again. It works. Yeah, and ignore the error in the end here. And I just noticed we don't need the device idle anymore. Let's clean that up real quick. Okay, that still works. Still throws us this error. But we'll fix that later. That is it for now. If you like what I do, consider tuning into my Twitch. I stream at 10 AM Central Eastern Time, which is 1 AM Pacific Daytime. You can also support me on Patreon. I've set up a new page. Supporting means getting access to the game code that I'm currently working on, which is Cake's Tower Defense. We added a new define in the build. We initialized most of the Vulkan stuff. We still need to do render pass and pipelines. We'll do that next, and then we draw a triangle. And over here we render. We can also do if it doesn't render properly, we return -1. Now it's time again. We git add, git checkout -b. And the next tutorial will be 03 Vulkan renderer init. We are going to do this 2 times. We check out the branch. We do git commit -m initialized Vulkan to do clear color on the screen. Then we push that. Git push -u origin 03 bull renderer init, and we are golden. And this is where we'll start next time. And then we specify sc info.pretransform is surface caps dot. Stop! Why would you do a struct? You dumb bitch! Image extend. Stop! Dot image. Image extend. Oh my. When creating the Swapchain images. Stop it with the fucking intelligence! You stupid bitch! Oh god, you're pissing me off! Stupid fucking program! Level count is fine! How long do you fucking need? God!